and welcome to Spotlight on Education. I'm Dr. Jon Kopko, Superintendent of East Brunswick Public Schools, and your host for the program. Today I'm in the studio with Dr. Beverly Finnegan, who is our District Supervisor of Mathematics and Basic Skills, and Kathy Wilker, who is our Mathematics Department Chairperson. I'd like to welcome you both. Today we're going to be discussing the mathematics curriculum in Churchill Junior High School and East Brunswick High School. And Kathy, I'd like to begin with perhaps you providing an explanation to our audience of the mathematics requirements and the courses that our students take to meet those requirements.
Well, Dr. Kopko, each student who graduates from East Brunswick High School must complete at least 15 credits in mathematics. That means that they have to take 3 full-year courses between grades 9 and 12. Most of our students, however, do go on and take at least 4 or maybe even more college preparatory courses. We have 3 college preparation sequences in the mathematics department. The honors sequence, college prep level 2, and college prep level 1. The honors program is designed for the mathematically talented student and involves a high level of mathematical rigor and proof. Students who pursue this curriculum should be highly motivated and strongly interested in the study of mathematics. The student in the honors sequence will go through Algebra 1, Geometry, Algebra 2, Pre-Calculus, which includes trigonometry, and a course in Advanced Placement Calculus. The Level 2 academic sequence follows much the same path, except they will not take an Advanced Placement Calculus course in their senior year. Rather, they will take a regular course if they begin the sequence in grade 8. The courses at this level do not have the same intensity and rigor that those at the honors level do. Students who elect to take courses in this sequence would be average or above average when we look at national scores. The third program we have is Academic Sequence Level 1. This is still a college preparatory sequence. However, it allows those students who have had less success with mathematics to build a strong foundation by taking Algebra 1 over 2 years. The students then go on and continue with an informal geometry course which de-emphasizes formal proof and relies on investigation to establish the material. Then they culminate with an intermediate algebra course. Finally, the mathematics department offers a 3-year sequence for the non-college bound student. The contemporary mathematics program informally introduces the students to algebraic and geometric concepts, as well as the collection, organization, and analysis of data through hands-on experience.
Well, Bev, there have been many changes in mathematics over the past few years. And would you tell us about how these changes have affected our mathematics program?
All right, there are really 2 major areas that have changed, one dealing with content and the other dealing with delivery. There have been new branches of mathematics discovered and explored because of the use of technology, and these topics are now available to us for inclusion into the curriculum. Students are learning more things at various grade levels because we found, one, they come to us with more mathematics and they are capable of understanding more sophisticated topics. The second that has changed is the delivery. We know that the classes are being taught differently. With the inclusion of student-centered activities and a lot more teacher involvement with questioning techniques, the students have been very active within the classroom and within their learning. They can discuss, they can do hands-on investigation, they can generalize, and they can then conceptualize their own learning through these hands-on activities. The technology has also added to the environment. The use of the calculator now allows them to explore and to observe and to generalize information beyond what they were able to do before we had these tools available to us.
Well, we do have tapes of several classes at Churchill Junior High School and also East Brunswick High School. And Kathy, could you give us a preview of what we're about to see?
On the tapes that we're going to look at, you will see clips from a variety of the courses that are offered from grades 8 through 12. Mainly, however, I think the important part is you will see the changing role of the mathematics student and the mathematics teacher. Students no longer just produce correct answers. You will see them routinely being asked to answer the how and why behind the problem, as well as to make their own conjectures and to verify their conjectures as how to approach a problem. Importantly, I think you'll see what Dr. Finnegan mentioned about the role of the teacher, the questioning techniques. The teacher in the mathematics classroom is no longer just a dispenser of knowledge. They now take on the role of being a guide, a facilitator of learning.
Okay, we talked about adjacent and vertical angles. The characteristics of adjacent angles are common vertex, common side, and they don't overlap. Let's look at the angles that I drew on the board and tell me, I'll label them, which ones have adjacent angles. Anthony.
B.
B, you would say B is an adjacent, 1 and 2, and the angle labeled B are adjacent.
No. A.
Okay.
A.
A, can you tell me why?
Because they have like a common vortex.
Okay,
Vertex.
they do have a common vertex.
They overlap.
They have common sides.
Okay, which side do they have in common? Notice I wrote common side and I wrote it singularly. Do they have a common side?
No.
Okay, so we're going to have to rule out A. So A, notice, got ruled out because it did not have a common side. Okay, let's have a look at B. Are angles 1 and 2 in B, are they adjacent angles? Danielle?
No,
Why not?
because they don't have a common side.
Good, they don't have a common side. Again, this got ruled out because there is no common side between A and B. You really can't make a mistake when doing the adjacent angle test. Run through those 3 characteristics. In order to be adjacent angles, the 2 angles must have those 3 characteristics.
I'd like your attention for a minute. This morning, we're going to take a little pair share quiz. And that means you'll work some equations out using the graphing calculator in a group. One of you will work it out, check the other one. Each of you share your answers, check your solutions, and just to start us off, I'll demonstrate one on the screen. Okay, I have 2 equations set up on the screen here. First one is 3x minus 2, and y equals 1/2 x plus 3. All right, just to refresh your memory on this, once you get the equations entered, you press the graph button, and you'll see the equations graphed on the screen. Now, the solution is the point where the equations intersect. So if you'd like to find the solution, you press the trace key, and you will see a cursor appear. You can see the little cursor appear. You've got to move the cursor with the arrow button, and you'll see it move up until you think that those 2 are at showing a point of intersection. At that point, you can see below approximately what the intersection points are. So the intersection to your problem are all whole numbers. So what you want to do when you get these as close as possible is to round these off and use these rounded answers to check back into your solution whether or not they are true actual values that solve that system. Okay? If there's a possibility on some equations, if the equations do not fit on the screen, you will need to change your window. You can change the window by pressing the zoom button. You can go down to zoom 4, which will change the window. And in this case, I made the window smaller. If you want to see the intersection a little bit better, you can make the window a little bit smaller. Okay, 1 second. Oh, there is one with no solution. That might be it. Goody. Yeah, there is.
All right, in the diagram, segment PA and segment PB are tangent to circles centered at O at A and B respectively. Okay, so there are 3 things we're looking for. Number 1, if the measure of arc AB equals 130, find the measure of angle P. Can we do that one?
Yes.
Yeah? Okay, how, Joe?
I use a theorem which says that the angle that is tangent to the circle with cutting off the arc is half the arc.
Okay, explain what you mean by the angle is tangent to the circle.
Oh, Well, the angle consists of two lines, and those two lines are tangent to the circle.
Okay, that's important. So the angle itself isn't tangent, right? The
No.
two segments are... Okay, good. So what theorem are we using there then?
I don't know, I have to look it up.
Okay, Brett?
Oh, could you
Let's see.
like draw two right triangles?
Can you draw two right triangles where?
Because PA from O to A,
Mm-hmm.
draw OA, and then an O to B, and then you draw OP. And you have two right triangles.
Okay.
And since those two triangles are congruent, the 130-degree angle,
So you want to draw them where? Right here?
yeah. And
It's
OP.
not really the same. It's tangent to
And angle OAB would be, AOB would be 130 because the
Why?
angle is equal to the measure of the corresponding line.
Okay, well, are we with him so far? Okay, he's using the fact that the arc is 130, so what kind of angle is that? Central angle, good, is 130 as well. Okay, so how are you going to find angle or...
If you draw OP, you have two congruent triangles, and that 130-degree angle is bisected. So you have a 90-degree angle and 65, so the other angle has to be 185.
Mm-hmm.
And since you have that twice, it comes up to 50.
Good, now Brett, you're absolutely right. Okay, does everyone follow what Joe is doing over here? Joe didn't go through all that, yet he was able to still come up with it. What was Joe using? Hold on.
Half of R1.
Yeah, and what tells us that? What tells us that that's going to be true, that the measure of that is going to be 1/2 of the arc? What theorem? It's not really a theorem, is it? I mean, don't we have a special kind of angle here? It's a tangent-tangent, isn't it? What do we know about the measure of the tangent-tangent angle? This is what Joe was trying to tell us. Justin?
It's half the measure of R minus near.
It's 1/2 the far arc minus the near arc. That's what we had established, right? So what is the measure of the far arc if the arc AB is 130? How do we get that? Irene?
360, since the entire circumference has to equal 360 degrees minus 130.
360 minus 130, okay. So that makes arc AX be equal to what? 230. Okay. And then arc AB is given to be 130. Now look at that, that's just arithmetic now, right? What does that come out to be?
50.
50, good. Now let's look at angle P. If angle P is given to be 20 degrees, can we find the arc? Well, we're going to just apply the concepts in reverse now. Jerry?
No, you can't, because you need to know like two things. Like you either need to know like angle P and arc AB, or angle P and arc AXB, or arc AB and arc AXB.
Absolutely right. I mean, we don't have enough information. It's not just a question of doubling it, because we're taking half of a difference. And we need a difference of two things that we don't have. So what are we going to...
Okay, we are reviewing the fundamental theorem of calculus so that we can do two free response questions. So what we're going to do at this point is review everything we know about integration and about graphing in groups in two free response questions, and then you are going to give it back to the rest of us. These are AP, 1995 AP questions, calculator active. So that's why you're in groups near your calculators, right? The same calculators are together. So I'm going to give you these questions. We will work in groups for about 10 minutes. I want you to give yourself 7 minutes for the first question, 7 minutes for the second question, and then we'll find some confident groups to present them for us.
That's why you're wondering.
That's good.
Right, and did you test for that?
Yeah.
How do you know?
Because if you plug, like say you plug in a -3, it's gonna square it, so it'll be 9.
Okay, I know you know. You have to explain to ETS that you know.
All right.
What could you do to show that you know?
See, so the x values goes on infinitely in both directions.
You could solve this is greater than 0.
Yeah.
You could graph your denominator, show that it's positive everywhere.
Oh, okay.
Okay, but pick something to show that you know
So
what
you
you're
can't just
talking
like
about.
plug in a negative number. And
No.
Okay.
That's not good.
That won't
Well,
work.
that's what I did.
I know. How do you decide if that can equal 0?
If x squared plus x equals 1.
Plus
negative 1.
Okay, and does it ever? How do you decide? What kinds of things do you have? Right, x squared plus x plus 1 equals 0. How do you do that?
You trace it.
You could trace it, you could graph it, you could use a quadratic formula, but you have to use something to show that that's always positive.
-2 something like that.
Why don't you look at this square root of x squared plus x plus 1 and try graphing it and see if you get all positives.
1 over the square root?
No, just the denominator, and see if you get all positives.
Well, we figured out that the domain is all real numbers since, first of all, in our function, the only way it wouldn't be all real numbers is when we set the denominator equal to 0. And once we did that, we figured out that there's no way that you can get a negative number under the square root. Since once you plug, even when you plug in negative numbers, once you square them and you add a value not squared, you get a positive number under the square root sign. Therefore, you can have all real numbers in your domain. For the second part, we just graphed it on our calculators, and that's the graph we got. And then it just increases throughout.
But to give an idea on what discrete mathematics is all about, what's really been covered, I've asked my students. This is probably a class full of East Brunswick's finest students. We have the heart of the academic teams, science teams, yearbook staff, varsity athletes, Model UN and Congress, etc. So this is quite a collection of people we have here. So we've kind of gone through some topics that we have discussed, and people have volunteered to just share just a comment on what particular thing that was about in the course. So a large part of our work involved graph theory. All different types of graph theory. Most of the graphs we look at, other students wouldn't even recognize as a graph. They're thinking of lines and parabolas and things. But we have some kind of different types of graph, some associated with relations. So let's have, I'd like you also to introduce yourself as you say something. Go ahead, Dimple, you can start.
Okay, my name is Dimple, and I'm going to talk about reachability graphs. And that's when you have a set of ordered pairs and you graph them. You graph them as something called a digraph, which uses arrows to indicate which numbers are paired with other numbers. And the reachability of this graph determines which part of the graphs are reachable from another part by means of arrows, which are called edges.
Okay, thank you. The idea is functions are special types of relations, but if we're really just interested in how, for example, how this computer communicates with that computer, we might be interested in what path the signal would have to go. So then we're talking about these diagrams. Okay, and how about Raji?
Okay, my name is Raji, and I'm going to talk about spanning trees. Basically, we talked about trees in this class, which is if there's a graph A, B, C, D, E, we have C, D, E. There's potential ways to draw this. If we have all the vertices connected, then we have a tree. But we cannot have a tree if we have a cycle of some sort, which is any type of ring. So we can form a cycle like this, we can form a cycle like that, we can form a cycle like that. Any one of those ways would disqualify this graph as a tree. So what we have to deal with is all the vertices are connected, but no cycles are formed. In essence, this graph being a tree itself is a spanning tree of itself in theory. If we added this edge right here, then this graph is no longer a tree, but the spanning tree of this graph would be only these edges. And that's the basic principle behind spanning trees, finding a tree within a graph which connects all the vertices, but uses edges only from the original edge set, which is made up of all the edges, and combines the graph in the manner of a tree, skipping over anything that forms a cycle. That's basically it.
Okay, so that we could use something like this maybe to save money. If we wanted to make sure we could hook up A to all of these things, but this, we could do that by bypassing that particular part of the graph. Maya, you want to have anything to add on that?
Well, I'm doing the roots of spanning trees, and basically for this tree you could consider any one of these points a root. And if you consider this as a root, then the levels below it would be the ancestors, and each level could be considered as descendants, and it's a singled out point of a graph.
We also looked at family trees briefly, and we had the students look into their future family trees, and we had some very good results on that. That was really, really enjoyable.
We took a little side trip off the book and to barcodes. Now, this is kind of big than you'd find in most supermarkets or stores, but they're very important. And what's important about them is the little bars on top can be read by a computer, making things a lot easier. But the real key to this is the little numbers on the bottom. For example, this is a UPC symbol, often found on most of your supermarket products, books, or many other things. They bring up prices. The first 5 digits are assigned to a specific company. For example, these digits could be assigned to East Brunswick High School. So everything East Brunswick High School made would have those 5 digits in front. And then the next 5 digits are the company can assign to specify what it would be. For example, 6 can mean science department and different things. So in those 5 digits would be encoded the price, how many ounces or what type of item it would be in the category the company would make it. And the interesting thing about this is the little number on the end. And that number is called a check digit. And whether you're doing zip code bars or ISBN bars or UPC bars, they each have a little check digit. This allows the computer or the person typing in the number, if they make a mistake, the computer will detect it, because by somehow adding or rearranging these numbers, it has to equal this check digit. And if it doesn't equal this check digit, the computer will not accept it. So basically, this is a good way to understand how computers work, and it makes life a lot easier for all of us.
Yeah, and we've also found.
It certainly is interesting to hear the students actually explain the work that they're doing. Bev, what does the future hold for our mathematics program and curriculum?
Well, one of the things that we'll see is a continuation of the expansion of curriculum. As you saw in the discrete math tape, we were looking at a new level of mathematics. Most of the mathematics that students have learned have dealt with situations on continuous types of numbers. Numbers like fractions and decimals, pieces of things. When we look at discrete math, we look at whole numbers, unique situations. The applications of those are numerous. If you look at the mailman, the route, the most expeditious route that a mailman may take is determined through the use of a discrete math. It's also determined where they should place their mailboxes to carry their mail or store their mail, based on which is the best place to be. Again, this is the use of discrete math. Color maps, figuring out what are the best colors and how many colors you would need to create a map, again, uses the concepts of discrete math. So all of this type of mathematics, which is really very new because of the use of the computer, we will see lots more of those types of topics showing up and being added to our curriculum. We know that the CBL, which is a computer-based laboratory unit that we have been using experimentally in one of our classes, helps children begin to understand what a slope really is. When they do an experiment of taking a car down an inclined plane, they begin to understand what happens when you make the slope steeper or less steep, so that they can get a sense of what that line as an equation really is. So those kinds of applications will be new and exciting and ways for students to really understand the mathematics that they're learning. We are also looking at new courses. A new AP statistics course is coming out, and we'll be looking at implementing that within the curriculum and within the next couple of years.
Okay, one final question for both of you. How can parents help their children become more proficient in mathematics?
Well, I guess when you think about the parents of children both at Churchill and the high school, one of the things that we'd really like them to continue doing is fostering that love of learning. The need for children to understand that they need to value a broad mathematical background, because life is really going to be very different when they're adults, and they're going to have to be lifelong learners. And if their parents support that understanding, it will become important, and they will feel comfortable in looking towards expanding their mathematical background. We also would like parents to continue to show interest in their children's success and their progress in their own courses, in their studies in mathematics.
Mathematics by its nature is a continuously building subject, and it's extremely important that the student progress on a daily basis. If a child is encountering any type of guilt, of difficulty, I think the parents should be encouraged them to seek extra help immediately, not to let it go. Most of the teachers at grades 8 through 12 are available to the students both before and after school for help. And another nice aspect at the high school is the math lab. Each day during the lunch period, students may use half or more of their lunch period to go to the math lab and receive individual assistance. So I would ask that the parents not let a problem go, that they encourage the children to seek help immediately.
Well, I'd like to thank both of you for being here today in our studio. I'd especially like to thank you both for just the wonderful and outstanding work that you've done in moving our mathematics program forward. Also to your staff for the excellent work that they're doing with the students. To our audience, I'd like to thank you for watching. This is our last show for the 95-96 school year. We will be back with you again in September with a new version of the Welcome to the East Brunswick Public Schools tape. During the summer, we will have reruns of some of the programs that were aired during the year. Once again, thank you for watching, and on behalf of the Board of Education and everyone associated with the East Brunswick Public Schools, we wish you a very happy, enjoyable, and safe summer.